Okay.
Okay, so let's now share. Here it is. Okay, so do you want to do the usual thing like we go through this? I had some students for the office hours today, so I think Ashley should join like later on. But and we went through the worksheet, so it was pretty hard, and it's always hard. So let's see. What do you say? You can go like an answer, and then I'll give feedback if necessary.
Okay. Thank you.
No problem. Did you try to do this before the meeting?
No.
Oh,
But
okay.
I read the chapter and I did the weekly participation.
Okay, good.
So, just each of the lengths would double in size.
Mm-hmm. Mm-hmm. So for example, 3 would become
6,
and 2 would become
4.
okay, fine. Good. So that's you just like redraw that, basically make it bigger. Okay, then let's answer the questions.
Okay. Which of the galaxies B through D increases its distance from galaxy A by the greatest number of light years during this time? It's going to be B because it has the greatest length to start off with.
Very good. Great. So then students 1 and 2, which one is correct?
Student 2 is going to be correct.
Yes, student 1 does not know math, right? So the student 2 is correct. Okay, very good. Fine. So it says since galaxy B was the farthest away from galaxy A initially, its distance will increase by the greatest number of light years. So that's what you concluded as well. Okay, very good. How about number 4?
Describe the relationship between a galaxy's distance from galaxy A and the speed at which the galaxy appears to be moving away from galaxy A. It's is it doubling if it's
No, it's just like the speed. What is the speed? The speed is, how would you define speed, like in physics or in like everyday life?
Kilometers per second?
Yeah, or miles per second. So it's basically like the distance that you go in time, right? So you already said that the galaxy that appeared to move the greatest distance, right, from the galaxy A was the one that was initially farthest out, right? So if you move the greatest distance in the same amount of time, you know, whatever is the time that takes universe to double in size, then you move the fastest, right? Or that galaxy moves the fastest. So what's the relationship between galaxy's distance from galaxy A and the speed? The farther out the galaxy is,
The faster it's moving.
exactly. Very good. Does that make sense?
Yeah.
Okay, good. Now, is that relationship unique to galaxy A, or would you observe the same relationship if you lived in one of the other galaxies?
You would observe the same relationship if you were living in another galaxy.
Exactly. If you move in to the galaxy B, right, still galaxy A would like move fastest away from you because it starts initially with the greatest distance. If you move to galaxy C, still A and B would be moving faster away from you than galaxy D, right? That's what you would see. So simply the relationship is not unique to galaxy A, right? But wherever you go, you observe the same relationship. Okay, what do you say about part 2? You can take some time if you want to read, and I'll wait.
Okay. it's saying that the farther the distance, the faster the velocity, and
Mhm.
that's the same law that I explained in on question 4.
Very good. Okay, great. So then question 7.
Imagine the Hubble plot shown in figure 2 represents a universe that doubles in size over a certain amount of time. Which of the Hubble plots shown in figure 3 and 4 below might represent a universe that triples in size over the same amount of time?
Mhm.
I think it would be figure 3, but I'm not really sure why.
Okay, but when you're looking at these graphs, okay, you're correct. So when you're looking at these graphs, what's the difference between them?
One one shows a shorter amount of distance and a higher amount of velocity.
Which
And
one? Number 2?
number 3, figure
Okay.
3.
So three, I mean, because you don't have numbers over here, you cannot really say, right? But what you can see over here is that these galaxies, right, are moving pretty fast with respect to each other, right? While these galaxies over here, they all move pretty slow, right? Slow velocities over here, as you can see, right? Or very similar velocity to each other. Does that make sense? So there
Yep.
is not much difference, like a speed of this galaxy compared to speed of that galaxy, right? While here you can see some will move like, you know, kind of a slowish, but the other ones will move like really fast. So, and here, like this one is like in the somewhere in the middle, right? Those speeds like, you know, slowly increase. So what do you say then? If this one doubles in some amount of time, then definitely like in the universe in which galaxies are moving faster away from each other, which is this universe, would then reach the greater size in the same amount of time, right?
Yeah.
That's the idea. While this one would take like a long time to reach basically that size.
Yeah.
Okay, good. Okay, so that's it. So this one, like, you know, so you can kind of see that this type of graph can also tell you kind of the expansion speed of the universe. Okay, and so now that is kind of explained over here or related to these graphs, like more mathematically. So you can read that, and then we can try to answer these questions.
So number 8 would be increasing with time.
So it's asking you what's the expansion rate, right? Is it constant increasing or decreasing with time? And here it tells you what? That expansion rate determines how fast the universe increases in size with time. And so this universe, they say, would have faster expansion rate than a universe that is doubling in size over the same amount of time. In a Hubble plot, the expansion rate is indicated by the slope of the graph, right? A steep slope, so that one over here, indicates a fast expansion rate, while a flat slope, like this one over here, indicates a slow expansion rate. Okay, so the expansion rate is given by the slope. So what, and do you know what the slope is? Did you, I don't know how far you went with math.
Yeah, it's I know what it is, but I can't
Okay, so
describe
it's
it.
kind of a rise over run, right? That's what
Yeah.
we call the slope. Okay, so would you say that the expansion rate for the universe represented in figure 2 is constant increasing or decreasing with time? So that's our figure 2, okay? So what's the slope of this line? Is it like a single slope or it's changing slope?
It's a single slope.
It's the single slope, right? So if the expansion rate is given by the slope, this graph has a single slope. So that means just like a number, it's a constant, right? So the expansion rate is constant then, right? On all of these graphs where you just have like a line has a single slope. So the expansion rate is going to be constant.
Okay, that makes sense.
Does that, so don't confuse like velocity. Velocity is increasing, okay? But the velocity is increasing at the same rate as the distance kind of increases, right? And that is given by the slope. So the slope is constant. It's the same kind of a rate of increase in velocity.
Yeah.
Okay, good. So number 9 then.
Rank from fastest to slowest the expansion rates of the 3 different universes represented in figures 2, 3, and 4.
Mm-hmm.
So 3 is the fastest,
Okay,
2 is the second, and 4th is the slowest.
very good. Okay, number 10.
If the expansion rate of our universe had been faster, would the universe have reached its current size earlier in its history or later? It would have reached its current size earlier in its history.
Very good. Okay, great. And you know what that means? Like I always say, like the universe started in the Big Bang, which means something like really small, right? Everything was close together and then it expands. So you move away and then you reach some size. So it's basically the same. Like, you know, you can think like you started from San Diego and you have to drive somewhere, right? The faster you are driving, the sooner you will get there, right? So that's kind of the same analogy that you can apply over here. So if we all start from the Big Bang, but then we expand faster, we'll get there basically sooner. Okay, good. Next one.
If the above Hubble plots figures 2 through 4 represent 3 universes that are the same size, which Hubble plot belongs to the youngest universe?
Mm-hmm.
It's going to be figure 3.
Because?
Because it's expanding the fastest.
Very good. Great. Okay, fill in the blanks.
For 2 universes that are the same size, the universe with the faster expansion rate must be younger than the universe with the slower expansion rate. The slope of the line in the Hubble plot of the younger universe will be steeper.
Good.
But couldn't it be the Hubble plot of the older universe will be flatter?
Yes, both are correct. Whatever you choose, okay.
Oh. All right.
Good.
13. On the blank graph in figure 5 below, draw a Hubble plot for which the expansion rate is 0.
Mm-hmm.
Just be a straight line across.
Very good. Just a straight line across, because then the slope is 0, expansion rate is 0. Okay, great. Number 14, hard.
On the blank graph in figure 6 below, draw a Hubble plot for which the expansion rate increases throughout the lifetime of the universe. Would it be just similar to graph or figure 2?
Well, you did say for all those like 2, 3, 4, right, that the expansion rate was constant, yes?
Yeah.
Okay, but now it's increasing throughout the lifetime, which immediately means you cannot have like a straight line, right?
Yeah.
Okay, good.
Would it be like a wave?
Like a wave? I don't know. Okay, let's come back to this question after we do like this question, the part 3, okay? Because that's
I think I know now.
Okay.
Would it be like the opposite of that?
Like the opposite of this?
Yeah,
okay.
Flip around.
Okay, let's go through this one and then we'll come back, okay? Then you can make up your mind. So here they want you like, draw a Hubble plot for which the expansion rate increases throughout the lifetime of the universe, okay? So even maybe, okay, let's talk about this. First of all, so it has to be a curve, as you said, okay? What does that mean? How does, so when you're looking at this graph, velocity and then the distance over here, lifetime of the universe, what does that mean? How does the time goes on this graph, the time axis, where would it be and which direction does it go? Where is now and where is like, Big Bang, for example?
The Big Bang is at the left and the bottom of the velocity and distance, like the little corner.
Like here, the origin,
Yeah. Yes.
that's the Big Bang.
Yes.
And where are we? Where is now?
Now is towards the end of it.
Here, over here?
Yeah.
Okay, let's go now do this graph and then we'll come back to that.
Okay. Recent observations indicate the Hubble plot for our universe actually looks more like the plot in Figure 7.
Okay.
Parts A through H all refer to Figure 7. Draw or write the additional information on Figure 7 as instructed. A. Draw a circle around the galaxies from which we receive light that was emitted closest to our present time.
Mm-hmm.
So it would be the dots that are closest to the end of the line.
Here?
Yep.
Here?
Yes.
Okay. I don't agree, but I'm going to ask you a question so you can realize. So what do you think, like this distance, how is that measured? Who measures the distance?
The observer.
The observer. The observer is us, right? On the Earth. So where is the Earth over here?
The Earth is at the origin.
Yeah, the Earth is over here at the origin, right? So if we measure the distance away from us, right? So these would be like, nearby things, and then these would be like really far things, yes?
Yeah.
So then draw a circle around the galaxies from which we receive light that was emitted closest to our present time. If you want to see galaxies in present time, where do you look? Do you look at the galaxies that are really far away from us or at the galaxies that are really close to us?
The galaxies that are close to us.
And why is that?
Because the universe is expanding and it takes time for light to reach us from.
Yes, very good. Okay, so it takes light to reach us. If the light is traveling like in a long time, like billions of light years to reach us, you don't really see those galaxies how they look now, but you see them how they look when the light was sent, right? And so that means like if you want to get light closest to our present location, you basically circle this thing, right? That's what comes from galaxies that emit light closest to our present time. Okay, and so that means then square around the galaxies from which we receive light that was emitted farthest from our present time, that would be here, right, at the other end.
Yes.
Okay, good. C?
Write the letter C and draw an arrow to the galaxies that are moving away from us with the fastest velocities.
Mm-hmm.
The square.
Yes, very good. That's just like reading the graph, right? They move like really fast, okay? And then we have D over here, right? Okay, next one.
Write the letter E and draw. Hold on, sorry.
Mm-hmm, mm-hmm, okay.
Write the letter E and draw an arrow to the graph where it has the steepest slope. That's the beginning.
Yeah, very good, right? E over here is the steepest slope. Why? Because simply the slope is that. It's pretty steep. And the slope here is almost like a horizontal line, right?
Yeah.
So so that would be then what letter? That's the next one, right? F.
Can you, or no, I got it. Never mind.
Okay. Do you see F?
Yes.
Okay, good. Right, the flattest slope is going to be here, agree?
Yeah.
Okay, great. Okay, write the letter G and draw an arrow to the portion of the graph that corresponds with the fastest expansion rate, okay? So where is the expansion rate fastest?
Close to F.
Well, think about it. What gives you expansion rate? How do you, from this graph, read the expansion rate?
Closer to E.
Okay, so why did you change your mind?
Well, because I thought that the farther away a galaxy is, the faster it's traveling.
Well, that is correct, right? But that does not tell you the expansion rate, right, of the universe. Because what this is trying to kind of get you to think is when you're looking at this, let's say galaxies over here, this is not like, the Andromeda galaxy. First of all, Andromeda and Milky Way are moving towards each other, right? They're not like, torn apart by the expansion of the universe. This really talks about galaxies that are very, very far away from us, okay? Like different like super clusters of galaxies. So when you're looking at these galaxies, okay, they're far away from us, okay? Like billions of light years away from us. So, so you can see actually that when you're looking at this, they move, the expansion rate of the universe, how fast they move from each other is greater basically, right, than what was happening over here, right? This over here, you look at the galaxies that are even farthest away from us, and that allows you to look back in time. That allows you to look at the much younger universe, right? Not at the universe now, but at the universe like, a long time ago. So that's what I want you to think, right? So where is the fastest expansion rate? We already said it's going to be here, right? This is the fastest expansion rate, and this is the slowest expansion rate.
Yes.
Okay, good. What's the next question? What do we have? Okay, can you read these questions and I keep this graph, or you just want me to go with you now?
I'll read the questions.
Okay.
But I'm still kind of confused on why I see on the graph that the velocity there's a steeper rate. But I'm still kind of confused on.
Okay, so this is what I'm telling you. If the velocity is like, high, you do understand that's because like, those galaxies are really far away from us, right? Simply there is like more space-time between us and those galaxies, and they're being pushed away from us by the expansion of that space-time at greater velocities away from us than the nearby galaxies, right? So if you want to like, you kind of think about this, like you point the telescope into the like, space. You don't know really what galaxy is close, which one is far, but you can distinguish which one is close, which one is far by their speeds. The faster speeds they have away from us, the further out they are, right?
Yeah.
Okay, very good. And that allows you, the further out they are from us, the earlier or at different times in the history of the universe you're looking at them. So if you select like galaxies that have like really high speeds, that means you're going to look at the galaxies at different time than if you select galaxies that have low speeds, okay? So selecting galaxies by different speeds actually allows you to select them by different distances away from us, and that allows you to look at the universe at different times, right? How the universe is evolved, how like it changed throughout the history of time. So let's say you select over here the fast moving galaxies, and then you can actually, if you fit this slope, or this line, then that tells you that these galaxies, you can conclude they are moving away from each other at lower velocities than galaxies at present time do that, right? That's what this graph tells you. The slope in particular time or at particular distances is related to the expansion rate, how fast galaxies are moving away from each other, right? And we can see that that's different in the past or in the early universe than it is now. Simply that's what this graph shows you.
Okay.
Make sense?
Yep.
Okay, good.
Thank you.
No problem. This is really confusing, I think. This graph, right, requires some thinking because, you have to, I know I spent like, when I've seen this first time, I spent like a lot of time thinking about this, right? Because it wasn't like something that really like strikes you. And this is like, the time goes like this then, right? This is the direction of the time, if you want, right? This is the young universe over here, the baby universe, early after the Big Bang. And this is the universe now, right?
Yes.
Okay, good. So you read the next question, then an answer.
Okay. G, you write the letter G, or no? Are we on?
Yeah, 16, I think, yeah?
Yes. (16) Based on the Hubble plot shown in Figure 7, would you say that the expansion rate of the universe is constant or changing with time? It is changing with time.
Because the expansion rate is given by the slope, and slope is changing over here. Every single point, right, has its own slope. It's not like a straight line, but it's the curved line.
Yes.
Okay, good. Next one.
17. Based on the Hubble plot in figure 7, the expansion rate represented by the motion of galaxies far away from us, faster than us, slower than us, or the same as the expansion rate represented by the motions of nearby galaxies. It's faster than us.
Once what the expansion rate, right, represented by galaxies farther away from us.
It's
Don't confuse the velocity of the galaxy with the expansion rate.
okay. That's what I keep on doing.
I know.
So it's slower than us.
Yeah, so the expansion galaxy for the galaxy farther away from us. So these galaxies, right? This is where you need to look, okay? So that's how you select what galaxies are far away from us, these. But then expansion rate is given by the slope. And the slope is pretty shallow, right? It's pretty flat over here. So that
Okay.
means like lower expansion rate, right?
Yeah, I
Okay,
get
good.
that now.
Okay, good. Next question.
Based on the Hubble plot in figure 7, is the expansion rate of the universe increasing or decreasing as time goes on?
Okay, good.
It's decreasing as time goes on.
Okay, well, how does the time goes on? Where does the time start? In the square or in the circle?
It starts in the square.
Yes, very good. So then when you go from the square towards now, is the expansion rate increasing or decreasing?
It's increasing.
Because?
It's the slope of the line is
Steeper and steeper and steeper, yes?
Yeah.
Okay, very good. Next one.
19. Consider the following debate between two students regarding their answer to a previous question.
Okay, I think now I can move it. You erase this and then, oh, okay, fine.
Consider the following debate between two of student one. The expansion rate of our universe must be slowing down as time goes on. If you look at the Hubble plot, you can see that the graph gets flatter. That means the farther away you look, the slower the expansion rate is. The rate at which the most distant galaxies are moving away from us has started to slow down, and eventually the expansion rate of nearby galaxies will also slow down.
So what do you think? So the expansion rate of our universe must be slowing down as time goes on. If you look at the Hubble plot, you can see that the graph gets flatter, okay? So the student starts from here, right? And then it's looking at the Hubble plot and says it gets flatter, right? And it says basically that as the universe evolves, right, becomes slower expansion rate. So that means the student starts with 0 time where? Here, right? Like this is the beginning of the universe and this is the direction of the time increase. Is that correct or it's not correct?
That's not correct.
That's not correct, right? The student forgot basically that, like, you know, the distance is related then to the time it will take light to travel, right?
Yeah.
So the further out something is, or the more light has traveled to reach us, the more back in time we are looking, right? So that student is not correct. How about second student?
The student 2 is correct because he's explaining the graph correctly.
Yeah, very good. Student 2 is correct. Okay, and so now if you go back to your plot over here, 14, right? Is that the last question? Yeah. Would you change something?
Yes.
Okay, what would you change?
I have to read the question again. it would, wait, oh, it would look like um, figure 7.
Yes, very good. Okay, great. So you're done with this one. Do you want to do some other worksheet?
Yes, please.
Which one? Look back time?
Um, yeah. Or
The other one?
how about or is the writing prompt, is it very hard or?
I don't know. Writing prompt is actually, I think, very simple. You can go back to your book and just reference all of these questions.
Okay, let's do the look back time.
Look back time, I think it's pretty straightforward. So maybe we can even do this like in 10 minutes and then have time for the other one as well.
Okay. So when the universe was 4 billion years old, Galaxy A was 3 billion light years away from Galaxy B, as shown below. Imagine that the universe is not expanding, so the distance between Galaxy A and Galaxy B would not change over time. A star explodes in Galaxy B, producing a large amount of light. How long will the light from the explosion take to reach Galaxy A? 3 billion light years.
Okay, rethink your question. I mean, you're rethink your answer. 3 is good, but then what? 3 billion?
Light years?
Light year measures what? The time or the distance?
The time.
Light year.
Distance.
Are you confident?
No.
What is the light year? Light year is the distance, right? That the light travels in 1 year, right?
Yeah.
Okay, fine. So how long it would take, you cannot answer in light years, right? But in years, you just need years, right? If you're measuring time, it's not light years, that measures the distance, the same way like miles measure distance. So you need years, right?
Yeah.
Okay, so what do you say then? How long will the light from this explosion take to reach Galaxy A?
3 billion years.
Very good. Next one.
How far did the light travel on its journey to Galaxy A? 3 billion light years.
Now, yes, light years, okay.
How old will the universe be by the time the light from the explosion reaches Galaxy A? It will be 7 billion years old.
Very good. Next one.
Because light takes time to travel from place to place in the universe, when we look at the night sky, we are seeing stars and galaxies as they appeared in the past. For example, if we see a galaxy 1 million light years away, we are seeing what the galaxy looked like 1 million years ago. We say this galaxy has a look back time of 1 million years. Look back time is the amount of time light takes to travel to us from a distant object.
Okay.
What is the look back time inhabitants of Galaxy A associate with Galaxy B when they see the light from the explosion? 3 billion years.
3 billion years. Very good. That's the light look back time. Okay, great. Okay, now we switch to the real universe.
While the light from the explosion is traveling from Galaxy B to Galaxy A, does the distance between two galaxies stay the same, become larger, become smaller? It becomes larger.
Yes, very good. So you imagine like a photon over here, right? Me leaving from the galaxy B. While that photon is moving through this space, the space is being stretched out, right, by the expansion. So the distance increases. Very good. Okay, it's number 6.
By the time the light from the explosion in Galaxy B reaches Galaxy A, is the distance between the galaxies more than, less than, or exactly 3 billion light years? It's more than 3 billion light years.
Yeah, very good. It's more. Next one.
By the time the light from the explosion in Galaxy B reaches Galaxy A, has more than, less than, or exactly 3 billion years elapsed since the star exploded. More time has elapsed.
Yeah, exactly, because light travels with the speed of light, but if it has more distance to travel, right, it will take more than 3 billion years. Okay, very good. Next one.
It'll be more than 3 billion light years.
Very good. So it will travel more than 3 billion years and it will cover more than 3 billion light years. Okay, great. Next one.
When the inhabitants of Galaxy A see the light from the explosion in Galaxy B, are they looking at an event with a look-back time of more than, less than, or exactly 3 billion years? More than?
Mm-hmm. Very good.
So for 10, you could just draw something that would explain that the universe is expanding.
Yes. So this is really interesting, when you think about it, like, we can measure the distance to the Andromeda galaxy, but when we look at this very distant galaxies, okay, so let's say you get the light from like in the telescope, and then you can see basically that the light, let's say, traveled like 3 billion light years. That means like initially the distance between those two galaxies was smaller than those 3 billion light years. But that means also right now that they're at much greater distance than 3 billion light years. And so that is basically why distance makes no sense. We never ever in astronomy talk about distance to like, this very distant object, but we only talk about the look back time. That's the only thing that makes sense. You get the light, it allows you to look back in past. Does it allow you to look at specific galaxy? Well, that galaxy was not, it's not there anymore. So that's why we don't talk about distance, but look back time.
Yeah.
Okay, good. So we have time if you want to go through the last one.
Okay. Student 1, let's say the light takes 5 billion years to travel from one galaxy to another. This means the two galaxies were separated by 5 billion light years when the light began its journey.
Oh, so there was more in that more in the look back time?
Oh, yeah.
Oh,
There's one more question.
Okay. Oh, yeah, I see on the other side. That's left for the drawing. Okay, fine. So what student is correct?
I think that's student 1 is right. If the light traveled for 5 billion years and the distance between the two galaxies.
Well, if the universe is expanding, is that correct?
No,
Okay.
because if the universe is expanding, it'll take more time than
Their initial separation, right?
yeah.
Okay, good. Good. So which one is correct then?
Student 2.
Is he correct?
Yes.
Okay, very good. Okay, fine. Perfect. So that's the expansion. Okay, so this is the last one. Oops, that's not what I wanted. Wait, this is what I wanted. Good.
So number 1, I would say no, because there's other galaxies that's light hasn't had time to reach us.
That, and also like if you think that there are galaxies, the age of the universe, right, is like 13.7 billion years. So like, everything that has the look back time of 13.7 billion years has reached us, right? But you do know that those galaxies, like, whose look back time is 13.7 billion years, they're much further out from us right now than those like, 13.7 billion light years, right? Does that make sense? Because if their light was traveling that much while the light was moving towards us, they were moving away from us, okay?
Yes.
So the light took 13.7 billion years to reach us. These galaxies are now way beyond, like, 13.7 billion light years away from us. So, so if you go back, if you're looking now, if this is the observable universe, yes, there are definitely now galaxies outside of this observable universe, right? And their light to reach us will take much longer time.
Yeah.
Okay, good. When it comes to cosmology, I think this is all like a little bit hard. It like, you have to think exactly what you're saying, but I think it makes sense. Whenever you think like, that the speed of light is finite, takes times to reach us. So what can reach us is simply determined by the age of the universe, right?
Yeah.
Okay. Did you like this chapter, by the way?
I did.
Okay.
But some things were kind of challenging, like some stuff with the Cepheids, and
Cepheid variables, yeah.
yeah, I found that kind of, I didn't understand how to tell the luminosity from the graph, and
That's okay. So basically there is that relationship for the Cepheids variables that if they have particular period, they have particular luminosity, right? And so you don't know their luminosity, but from that graph, you can figure out what the luminosity is. What you can see is the brightness. And so whenever you know the brightness and you know what the luminosity should be, you can figure out then the distance to those stars. That's the whole idea. You don't have to know more than that.
okay. Yeah, I did like this chapter, though. It's kind of interesting.
Yeah, yeah, good. I'm glad. I like it as well. I really like the cosmology part. Okay, so that's the answer to the first question one. How about question two?
Draw a circle around galaxy X that represents its observable universe.
Mm-hmm.
Um,
I can do the circle. You tell me what to do.
would it be similar to what the circle already is, just moved over, and that's galaxy X is in the center?
Yes, very good. Great. So basically, like, because the galaxy X is like on the our edge, right? The observable universe should be exactly the same, like this sphere. This is horrible drawing, but basically you get the point, right? It's
Yeah.
centered on the galaxy X and it's the same size sphere or circle like this circle over here. Okay, good, great. Is that size of this universe different than the observable universe for the Earth?
No.
Why not?
I don't know, actually.
You're correct though. So, and you sounded very confident. So there must be a reason why you said that.
Because I don't know, like light has a certain
Yeah.
certain finite
You're
time.
correct, right? It's all about the light. Light takes time to reach you, right? How much time is available? Whatever is the time between Big Bang and now, which is 13.7 billion years, right? So they're exactly the same size. They're basically the size of like 13.7 billion light years look back time, both of them, right?
Yeah.
Okay, very good. Okay, let me raise this. Okay, and then we can move to the next page. Okay, very good. Next page.
Student 2 is correct.
Very good. Student 2 is correct. Okay, great. Okay, let's see now the balloons. By the way, did you prefer like the balloon analogy for the expanding universe or the raising bread?
The balloon.
Okay, I like the raising bread more, but that's okay. Okay, let's see now the balloon.
Do objects, light, or events in the entire universe also exist inside or outside of the balloon's surface in this analogy?
It gives you the answer kind of here, right? In this analogy, the space and time of the universe are modeled by the surface or skin of an expanding balloon. The entire universe exists on the surface of the balloon, only on the surface of the balloon, right? And the
Yeah.
light can only travel on the surface of balloon. That's why I don't like this kind of analogy, right? Because for me, it's not that like kind of intuitive, like the raising bread. So you're only on the surface, right?
Oh, yeah.
Okay, fine. So do objects, light, or events in the entire also exist inside or outside? No, the whole universe is on the skin or surface of the expanding balloon, right?
Yes.
Okay, if you were to travel from galaxy to galaxy along the surface of the balloon, would you ever encounter an edge?
No.
Never. Very good. I mean, that's kind of what they're kind of hitting over here. Standing here, this appears for you to be the edge, but it's not the edge, because if you're galaxy X, you see completely different set of galaxies over here, right? But you don't see these galaxies. But it doesn't mean that beyond your edge, the universe does not exist. It does exist. You just cannot see because of the finite speed of the light, right?
Yeah.
Okay, good. So number 7.
If you were to travel over the entire surface of the balloon universe, would you ever find a location that is the center of the entire universe? No.
They're very good. That's why this is good. Actually, the only thing why I like the balloon analogy is because balloon does not have any center, right? And when you think about the Hubble's law, that's the first thing that we did tonight, right? Whatever like galaxy you moved yourself to, not just that galaxy A, but you went to B, C, D, E, you look at the universe, you observe exactly the same. Everything moves away from you. So there is no central point, right? A unique point from which everything moves away. Everything moves away from every single point, right, in the universe. Does that make sense?
Yes.
Good. Okay, student 1 or 2.
So student one is wrong from the first sentence because they're saying by definition that the balloon doesn't have
Uh-huh.
a center or an edge.
That it does have, right? That's what they say, center and the edge. What does the student 2 say?
The surface of the balloon is supposed to be the entire universe.
Mm-hmm. So is he correct?
Yes.
Then it's she. Okay, so she's correct. Number 9.
The two balloons on page 2 represent the universe at different times during its history. Draw an arrow underneath the balloons that points from the earliest time to the latest. Label the ends of the arrow with the words earliest and latest.
Okay, so balloons on page 2 represent the universe at different times during its history. Draw an arrow. Okay, the earliest and latest. Okay, so you have 3 balloons. Which one is earliest and which one is latest?
The smallest one is the earliest, and the biggest one is the latest.
Very good, because the universe started much smaller, right? And as the time goes by, the universe expands and becomes bigger, and the space between the galaxy increases. Okay, very good. Okay, and then?
Would your answer to the previous question be the same regardless of the galaxy in which you live in, or would it change depending?
No, the previous question was, imagine you lived in a galaxy on the surface of the balloon. As the balloon expands, would all the other galaxies appear to move toward you or away from you?
Away from you.
Away from you. Is that like really easy to see here? Maybe, right? If you place yourself here in this galaxy, like now, and then the next time, do they all move away from you? Yes, they do. Like the distance increases, right, between all of you. And then the next question is like, would you observe the same thing even if you move to this galaxy? You would, right? Initially, everything is closer to you, and then everything is like further out from you. Make sense?
Yes.
Okay, good. So those were these 2. Okay, so question 12 then.
In this analogy, do galaxies move relative to one another because they are traveling across the surface of the balloon, or do they move relative to one another because the balloon is expanding? They move relative to one another because the balloon is expanding.
Yes. And let's go back to the balloons. So when you look over here, right, see how they did like a really careful job that all of these galaxies, they remain the same size, right, as the universe expanded. So the galaxies are not stretched out by this expansion of the universe. And that's important actually, because that's the reality. When you think about the Milky Way is in the universe that expands, but we are not stretched out by the expansion. The stars are not moving further out from each other because of the expansion. Gravity still dominates, right, on the scale of a galaxy. So the size of the galaxy remains the same, but what is actually expanding is this like space between the galaxies. So the expanding space pushes galaxies away from each other, but they remain their size, right? And that's what you can see clearly here.
Yeah.
Okay, good. Okay, and then we have the last question.
Okay, so for A, the universe has no center.
Mm-hmm.
That is captured by the balloon.
That is captured if you stick with their kind of a definition, right? That the universe is on the skin of a balloon, okay? Right? Because I mean, there is like a center of the balloon.
Yeah.
Okay,
Yeah.
fine. That's why I don't like it, because yes, you have to keep in mind that they define the universe to be on that skin or the edge of the balloon, okay? So then, yes, it's correct that that skin or edge does not have the center, okay? And then how about B?
The real universe has no edge, which is correct.
Yeah, that is captured by that model, okay? And then?
The universe is expanding. It is captured.
It is captured, very good. Because you can blow the balloon and expand it, okay? D?
The real universe is not round. It is, wait.
So this is the fact. The real universe is not round, okay? But when you're looking at the balloon analogy, what do you see? It looks pretty round, right?
Yeah.
So that's not okay, okay? So to think about like our, universe, you need to do, think about like ginormous, huge balloon, okay? Where these like local things over here will appear like pretty flat. Does that make sense? So this is the statement, this is the fact. The real universe is not round, okay? So it's pretty flat. Is that captured by the balloon analogy?
No, it's not captured.
Because balloon is pretty round, right?
Yeah.
Okay, good. E?
The real universe expansion does not cause galaxies to change in size. Well, the picture shows that. I don't know if an actual balloon would show that.
Yeah, the picture is good, right? But if you put like little dots on a balloon and then you start like blowing that, those dots are going to increase in size, right?
Yeah.
And they should not. The expansion of the universe does not affect the size of galaxies. So kind of a fails with that as well.
Yes.
Okay, good. And the last one?
The real universe is 4-dimensional, 3 dimensions of space, and 1 dimension of time.
Mm-hmm.
And that's not captured.
Mm-hmm. Very good. That's not captured. Very good. Ashley, are you with us?
I am. I almost forgot about it.
That's why I sent the reminder, but we went actually through this worksheet that we didn't get through today, and I recorded everything. So I'm going to post the recording.
Oh, you're going to post it?
Yes.
Okay. Thank God.
Okay, good. I know. Saved you.
Yes. Thank you.
Okay, good. Any more questions?
No.
No, Ashley, do you have any question?
I haven't really looked over this last part yet.
This making sense of the universe and expansion?
Yeah, the beginning, like Hubble's law and all that, makes sense to me as much as it can.
Okay. So we went, actually, Jonathan and I went through all three tonight, and I have recording, so that will be posted.
Okay, awesome.
Okay, good.
Thank you so much.
Oh, that's it. So no question.
All